So let me start by thanking the organizers for the opportunity to present this work here. So Aloisio Araujo was scheduled to talk, but he wasn't able to come, and I'm going just to replace him today. So this is joint work with Aloisio Araujo from IMPA, Alberto Pinto from Porto, and Choubdar from Porto, and Wilfredo Maldonado from the Catholic University of Brasilia. Okay, so I'll start by providing a brief overview of some previous results, and then I'll move on to the framework I'm going to work with, and then I'll introduce the selection criteria for this refinement of equilibrium. Then I'll kind of explain the main results we obtain and how they are related with some topics in dynamical systems. And then I'll try to provide two examples to motivate and to convince you that the results are relevant. And right at the end, time allowing, I'll provide an alternative selection criteria, which is analogous, but it has a slightly different point of view. Okay, so let me start by mentioning that the multiplicity of equilibria is a feature of dynamic rational expectation models, and that certain equilibria are linked with the existence of stationary sunspot equilibria, a kind of equilibria that I'm going to look in detail here. Then it's known that the existence of indeterminate cycles for the dynamics of some backward perfect foresight for some dynamics on some economic models that I'm going to introduce soon implies the existence of this stationary sunspot equilibria. And then the steady state indeterminacy implies the existence of this stationary sunspot equilibria with finite support. This is a kind of local sunspot equilibrium, and I'm also very interested in this on chaotic sunspot equilibria arising from certain maps describing the evolution of an economy which exhibit chaotic deterministic dynamics, and this is based on a result from Araujo and Maldonado from 2000. Okay, so our goal with this paper is to propose a selection criteria to refine the multiplicity of equilibria in some economic models. And our main result is for a large class of models that I will describe very briefly. The selection criteria will hide one of the following: either a determinate cycle, or a chaotic sunspot equilibrium, or a chaotic backward perfect foresight equilibrium path, which can be seen also as an equilibrium. And this is done in terms of the measures that we find by looking at perfect foresight equilibrium paths. So the main tool to obtain this description is the stochastic stability of chaotic dynamical systems, which is a theory that started being developed on the 70s with the introduction of the concept of stochastic stability by Kolmogorov and later developed by CUNY. And later on, this was developed by Young, Kiefer, and Katok and Kiefer for uniformly hyperbolic dynamical systems, and further on down the road by Baladi and Viana on a result regarding the strong stochastic stability of unimodal maps that are no longer uniformly hyperbolic. And more recently, there's a result, a very remarkable result by Avila and Moreira. Avila is in fact one of the Fields Masters, one of the 2014 Fields medalists, regarding the stochastic stability of very large classes of unimodal maps. Very good. So the models that I'm going to consider are one-step forward-looking economy models with an equilibrium condition of this kind, where xt is just a state variable. It's the value of the state variable at time t, and x tilde, so x tilde will always, or the tilde will always denote a random variable. So x tilde t plus 1, it's a random variable representing all the possible values that the state variable can take at time t plus 1, so the next step. Then et will denote the mathematical expectation with respect to some measure mu t or mu t plus 1 that describes the possible, the distribution of the future values given the information at time t. Okay, so given this kind of models, we defined the backward perfect foresight map to be a map phi, which is defined on some intervals of real numbers, which I'll denote by capital X, satisfying this condition. So the interpretation is the following, is that if we know the future state of the world at time t plus 1, we can find the, with certainty, so if the measure here for the expected value is just a Dirac measure with mass at x, then you can work out the present state value for the state variable using this function phi. So it gives you a way of going back in time. So knowing the future, we know the present value. So now, let phi, so we'll denote this, the backward perfect foresight map as phi throughout the rest of the talk. So let this map phi be defined on an interval of real numbers. Then we call a perfect foresight equilibrium path through x naught, a point in this interval x, to a sequence, to any sequence in the interval x, such that the following recursive relation holds for every positive or non-negative integer t. So it's a backwards recursive relation. So you start from some point xt or xt plus 1, and you, under iteration by phi, you move backwards in time. Then cycles and steady states are very conveniently defined in terms of this map phi. So just a k cycle is just an orbit for this map phi, which is periodic with period k. So if you start at some point, after k iterations of this map phi, you get back to the same point. So it's a closed orbit. And a steady state is just a periodic orbit or a k cycle with period 1. Okay, now, an indeterminate cycle is a cycle such that every neighborhood of it contains a continuum of perfect foresight equilibrium paths. And if this condition does not hold, then the cycle is said to be determinate. And a simple result says the following. If x star is a periodic point of phi with period k, meaning that the orbit of phi through x star is a k cycle, then if the derivative of the backward perfect foresight map at x star has absolute value larger than 1, then the k cycle is indeterminate. Meaning that when you look into the past, if the orbit is unstable, then you have an indeterminate cycle. If you look forward, and then you have stability, and then you have convergence to it. Yes, please?
So shouldn't that then be the phi k, the kth iterate of the map instead?
Sure. Thank you. Yeah, it's phi k. So I need to look at the derivative of the map phi k. So I missed the k. Thank you very much.
And you just need to look at the single point in that orbit?
Yeah, because all the others will have, all the other points in the orbit will have the same derivative. It's a periodic orbit, so you can produce an argument and you start at one point, then you are mapped into each one of the others. So the derivative at every point, the derivative of phi k at every point of this k cycle will be exactly the same.
And why is that?
Because it's a periodic orbit. Okay, it's just a consequence of the chain rule. Phi k is just the phi composed with itself k times. If you differentiate and take the chain rule, that the result will hold. I can do the computation at the end if you like. So they all the same. So you only need to check for one of the points in the orbit, not all of them. This condition. Okay, so just very quickly, a simple example leading to the kind of maps that we are interested in. It's an overlapping generations model with linear production and future consumption. So let's just say that X units of labor produce X units of good, and that units xt produced at period t are used for consumption in the future, ct plus 1. Then the agent's preferences regarding labor supply, denoted by x, and consumption, denoted by c, are described by an utility function of this form. So if you are given the current price, P of t, and the possibly random future price, Pt plus 1, then what the consumer is looking for is to solve this maximization problem, to find his consumption plan, subject to some constraints saying that if he earns a quantity Ptxt at period t, then is allowed to spend the corresponding quantity in the next period of time. So if we combine the first order condition for that optimization problem with some monetary equilibrium condition, then we can reduce the first order condition to something of this form. And it turns out that the map phi here is the backward perfect foresight map for this particular problem. It's just the famous logistic equation, which is something like this. This is one of the most widely studied maps in discrete time dynamics. It is a chaotic map. It has infinitely many periodic, repelling periodic orbits. These periodic orbits are dense on the interval from 0 to 1. It has amazing properties. Okay, so in particular, it has a repelling fixed point here on the intersection of the diagonal with the graph of the function. And if you look at the second iterates, then the second iterate is the graph plotted in blue. Then the iterate, the intersections with the diagonal will give you the periodic points of point 2. So in this case, you have the fixed point here at 0, another fixed point there, which are also fixed points for the second iterate. And then you have a single orbit of period 2, which maps this point to that one, back to this one. Okay? So, good. So now let me move to the concept of sunspot equilibrium. So again, capital X denotes an interval. B of X denotes the Borel subsets of X. P of X denotes the set of probability measures defined on the Borel sets of X. And a transition function is just a map from X Cartesian with the Borel sets of X into 0, 1, such that when you fix X and you let this be a function of the Borel subsets of X, then this is just a probability measure. And if you fix the set A and allow this to depend on X in capital X, then this is just a measurable map. Then a sunspot equilibrium is a pair of a subset of capital X, which we'll denote here by X naught, and this transition function defined on X naught and the Borel subsets of X naught, such that the equilibrium condition holds when we replace the measure regarding the future state of the world by the one defined by this transition function Q at a point X, and there exists at least one point X naught for which Q evaluated at X naught is not a Dirac measure, meaning that this is truly stochastic. It's not just deterministic. Then we say that this sunspot equilibrium is stationary, and this is key. I will make use of this notion later on. If there exists a probability measure mu for which a condition like this holds. Okay, so mu is left invariant by applying the transition function Q. Okay, and under appropriate conditions that I'll describe right now, Araujo and Maldonado proved that the sunspot equilibrium arises, or a stationary sunspot equilibrium arises, for one-period economies with chaotic backward perfect foresight maps. Okay, so what is this? So let's phi be from X to X be a unimodal map with an absolutely continuous invariant Bowen-Ruel-Sinai measure, mu. So this is a probability measure with some properties. In particular, it's absolutely continuous over a finite union of subintervals of X. We say that mu is invariant under phi, the backward perfect foresight map, if it preserves the measure of sets under the pre-image by phi. And we say that the Birkhoff ergodic theorem tells us that if mu is an ergodic measure for the backward perfect foresight map, then for almost every X in A, the space average of A, given by mu of A, is equal to the time averages computed along orbits of phi. Okay? Then the theorem by Araujo and Maldonado from 2000 says the following. So if you let F and G, so this is just a version for unimodal maps. The theorem is more general than this. But if you allow phi to be a unimodal map, and something like this, and if you, so this is phi, if you allow, so this is not one-to-one, so you can define locally two inverse maps denoted by F and G. This also defines a partition of your set into two subsets, A1 and A2, on which F and G are defined. Then, under some conditions, which is pretty much requiring that the map phi, the backward perfect foresight map, admits an absolute continuous invariant measure, mu. Then there exists some subset x naught of x, which is a finite union of intervals, and therefore it has positive Lebesgue measure, such that a transition function like this, where this denotes Radon-Nikodym derivatives, determines the stationary sunspot equilibrium on the set x naught with stationary measure mu. So the support of mu, it's not finite. It's a set with positive Lebesgue measure, and it plays a key role the fact that phi is chaotic and has an absolutely continuous invariant measure. Okay, so now to our selection criteria. So let epsilon tilde be a sequence of independent and identically distributed random variables with common distribution, so they are identically distributed. So common distribution with density theta epsilon, and this has support on a small interval from minus epsilon to epsilon. The associated small random perturbations of a perfect foresight equilibrium path is a sequence of random variables x tilde which satisfy this recursion. So they are obtained from a perfect foresight equilibrium path by allowing a stochastic perturbation to act on each term. So each time you start from a point, you iterate the backward perfect foresight map, and you add a noise, random perturbation. Then you pick this point, iterate the map again, add another random perturbation. And you keep doing this. So instead of performing a deterministic perturbation of the map phi, you are performing stochastic perturbations of all trajectories of phi. And distributions satisfying these kind of conditions are easy to find. You can just think of the truncated normal density on the interval minus epsilon to epsilon, or the uniform density on the on the same interval. And on the examples that I'm going to show you later, I'm going to be using a uniform density on some small interval like this. And possible sources of randomness can be obtained from rounding and chopping errors or evaluation errors for the state variable at a given time. So we lack precision in measurement, so we never know the actual value of this, of the random variable. Or we can acknowledge that our models are not precise enough, and there may be uncertainty in the way we define the actual model, or the parameters of the model. Or it may be that the parameters of the model are changing randomly with time. As time evolves, the parameters may be changing with under sources that we cannot control. Now, this stochastic process has a transition function that can be defined like this. It's the standard way to define a Markov process. And you can define this transition function in terms of the density function theta epsilon that described. So you completely know the deterministic dynamics of the backward perfect foresight map. And then you can use the density theta epsilon for the random noise to induce a kernel like this, which describes you the transition function. So you have a transition function, and if epsilon is small enough, then this stochastic process is stationary, and it has a stationary measure satisfying this condition. Okay? So this is one of the key ingredients to state our selection criteria. The next one is the empirical measures. So yes, please?
When does this phi function exist?
This p function exists always. So as long as I have a map phi, theta epsilon, theta tilde, epsilon tilde is just a sequence of independent.
So if I have a general some dynamic rational expectation model, can I find the phi always?
Well, no. For the phi you need conditions on the initial model. So if you allow me to go back, so for the phi to be well defined, you need to be able to solve this equation for phi. So phi of x is in fact f minus 1 of g of x. So f needs to be an invertible function.
So
for instance, you need to start by 1.
do you have some existence result for phi? Because all the results.
Under appropriate conditions on F and G, you can obtain this, and I'll show you a couple of examples where it exists. So sure. So the theorem is like this. So allow F to be a one-to-one function. Then phi of x exists and is well defined as phi minus 1 composed with G for any G, a well-defined function. Is that reasonable? That's just a standard existence result. Okay. You have a question?
Maybe I can wait, but I was just wondering, so if you start with your star equation,
Yep.
you could think of under some conditions you can get that decomposition into the phi plus an epsilon shot.
Yes. So for instance,
Without appealing to these rounding errors or something, it could be a fundamental which admits this kind of decomposition.
in terms of the epsilon.
Yeah.
Yeah, but then you yeah. So what I want to do is start from an equilibrium, well, this perfect foresight equilibrium path, and then I want to add this noise, acknowledging that the model may not be perfect a priori, and I add this noise, and I see what.
It's those words that are outside the theory.
Okay.
Like everything you said was consistent until you got to that kind of loose talk about that epsilon. You know that it could be like 7 different things.
Uh-huh.
I think that's what.
It's acknowledging it's very much done in physics and biology and other areas. You start from a model. The model is not a complete description of reality.
But I want to go the other way. Start with a stochastic model and then take a deterministic one. Right?
That's what I'm going to do. I'm going to this.
No, but you're starting with the stochastic, then you're looking at it.
No, starting with
and then
deterministic.
you're adding back some other deterministic.
No, this model here is deterministic.
Star on top is stochastic.
It's stochastic in the sense, but you're completely sure about what mu is. You see? So you know x of t, and you know the measure mu for the next instant of time, mu t. Mu t gives you, there's a measure that you know at t that gives you the probability distribution for x tilde. Okay? So this gives you this model. Okay? So to some extent it's deterministic in the sense that you know this mu of t. And even though mu of t is, okay, so let's call it stochastic because it depends on probability measure. But it determines a deterministic backward perfect foresight map. So when I say this when I'm referring to this as deterministic, deterministic is in the sense that phi is a deterministic function. Okay? Then I want to look at the robustness of the dynamics of this map phi and the random perturbations. Okay, so I acknowledge that when I introduce a random perturbation, this is no longer an equilibrium. So I'm going out of the equilibrium. But then what I'm going to look is, what are the behaviors, the statistical behavior that still persist as I allow the perturbation to go to 0? Is that okay? Okay.
So this is essentially asking what is a robust prediction of that model.
Yeah.
But if the model were literally right, it would still be a reasonable equilibrium.
Yeah, the point is that there's multiplicity of equilibriums. In fact, when I look at these chaotic backward perfect foresight maps, there are different kinds of equilibrium, and there are infinitely many equilibrium. So I'll show you to this in a moment. So there are infinitely many equilibrium, and this criterion will select one which is connected with the past history or the recorded history of a backward perfect foresight map. It won't be always one, but it will select a few with some properties among the infinitely many possible equilibrium.
In the spirit of global games.
Somewhat. Okay, so I'll show you. So we'll have infinitely many cycles. So for these unimodal maps, we'll have infinitely many cycles. And we will have infinitely many perfect foresight equilibrium paths, which are chaotic and therefore are dense over an interval. And on top of that, on these repelling cycles, we have local sunspot equilibrium, also in infinitely many, an infinite number. And we also have chaotic sunspot equilibrium. And this criterion will point out to some of these equilibrium or equilibria that are consistent with some history that we keep, some record that we keep of the iterations of phi as the limits of the random perturbation goes to 0.
If some were very small.
Epsilon is very small, yeah.
No, I mean the sum.
The sum?
S-O-M-E. I'm sorry, if you had a drastic reduction, that would be a big sum. I'm sorry.
I don't get it.
This is going to be victory. You use the term, you're going to have this big set of things.
Mhm.
There's lots of equilibrium.
Yeah.
Then you're going to do this refinement.
Yeah, that's
And
what
you
I mean.
said that only some will survive.
Sure.
And I want some to be 1%, not 98%.
Yeah, I'll remove a lot of them.
Yeah, that's all.
Yeah, that's the goal. That's the goal. That's what the statement of the main theorem says. Yes.
So you said you add some small perturbation. Is small perturbation is something you add, or it is something you can find from the given model?
It's something that I add. It's exogenous, and I was just motivating it. But if you don't agree with the motivation, then just allow me to add this noise exogenally. It's exogenous to the model.
So it's like you shift that phi map on the
Yeah.
board a little
It's
bit, or?
very good, yeah. So what I do is I start from a point X. I find the image under phi. So I get a point here. Now to this one, I add or subtract a small point epsilon. I identify it back here, and I iterate again. Then again, I kind of add a random noise epsilon. Every time I compute an iterator phi using the initial model, I add or subtract a noise with at most size epsilon, where epsilon is very small. Then I'll add epsilon goes to 0. Okay? So where are we? Okay, so we were here. So the selection criteria. So let nu epsilon be the stationary measure associated with the stochastic process defined by these random perturbations, small random perturbations, and let mu epsilon n be the empirical measures be defined by a trajectory of these perfect foresight equilibrium paths when I add some noise. Okay? So I'll say that an equilibrium is selected by the criterion of the small random perturbation of the perfect foresight equilibrium path if its stationary measure is the limit of the empirical measures mu epsilon n as n goes to infinity, meaning that the history it becomes infinitely long, and epsilon goes to 0. The size of the noise goes to 0. Okay, so that's one important point. So I look at the empirical measures, which is something that I can record by looking at the iterations of phi and adding some noise, and then I look at the limit as n goes to infinity and epsilon goes to 0, and I look at the measure that I obtain in the end. This measure will be compatible with some equilibria, but not all of them. So this measure will tell me what is the refinement that we can make to our list of equilibria. Okay, so we will work with maps somewhat like this. They are C-free. They are defined on an interval of R. They have a non-degenerate critical point, so it's non-flat here. That's what I mean. They have a repelling fixed point at 0, so they start growing more than 1, so the derivative of 0 at 0 is more than 1. And they have a negative Schwarzian derivative, which is a technical condition which means something like this. You have some sort of uniqueness of attractor. So if you have an attractor, the attractor is unique, meaning that if you have an attracting case cycle for the backward perfect foresight map, this is unique. Okay? And moreover, the critical point will be attracted to this case cycle. Then it is known that unimodal maps on this class belong to one of 3 types. They are either hyperbolic, meaning that they have one periodic attractor. This is the unique. If they have one, this is unique. And the basin for the basin of attraction for this periodic attractor is open and dense and has full measure. So everything except for a set of measure 0 corresponding to other repelling attractors is attracted to this point, to this orbit. And this periodic attractor and its basin are stable under deterministic C1 perturbations. Okay, so it's a very robust property to have, the fact that phi is hyperbolic. A second case is that phi is transitive on some finite union of intervals. And this is what we usually think of when we talk about chaotic maps. So there's a map there's an orbit, or almost every orbit, will be dense on this finite union of intervals. And therefore, this orbit will give rise to a stationary measure, mu, which is absolutely continuous. Then you have more properties. The map phi has a Lyapunov exponent, a positive Lyapunov exponent, meaning that you have exponential divergence of orbits. But one thing that we have is that phi may be unstable under deterministic perturbation. So you may introduce a very small deterministic perturbation, and you get to an hyperbolic map phi, meaning that this property 1 is open and dense in the set of maps. 2 is not open. Okay? But there's still a lot of maps of this kind. The third kind is of the maps that are infinitely renormalizable. These are somewhat similar to 2. They are still chaotic, but instead of having an attractor, which is a finite union of intervals, and therefore they have positive Lebesgue measure, they are easy to see even when doing numerical computations. What happens is that the attractor is a very small set with Lebesgue measure 0, which turns out to be a counter set. So focus mainly on 1 and 2. Especially because there's a remarkable theorem by Avila and Moreta that tell you the following thing. For a large class of unimodal maps in this family F, and I need to fix some degree of smoothness, in this case they are at least CR, or, well, 3 times differentiable or more. So for generic families, topologically generic families of unimodal maps, which are on this family F, meaning non-degenerate critical points and negative Schwarzian derivative. You can even drop this condition on negative Schwarzian derivative. Then almost every non-hyperbolic parameter satisfies 2 conditions, and these 2 conditions means that you are in 2. So either you are in 1, and this is an open and dense set, or for almost every other parameter, you are in 2. Okay? So 3 has measure 0 on parameter space. So 1 and 2 have full measure. So you are always at 1, or if 1 is not full measure, then 2 is positive measure. So 1 is large from both a topological point of view and a metric point of view, and 2 is potentially large from a metric point of view. And that's what I'm going to show you. There are conditions that ensure that 2 is large from a metric point of view, and there are a few examples that allow us to see this. So our main result says the following thing. For topologically generic k-parameter families of backward perfect foresight maps, coming out of the model that I described right at the beginning, belonging in this class of unimodal maps F, then the small random perturbation selection criteria will select either a determinate cycle, meaning an attracting cycle for the backward perfect foresight map, or for Lebesgue almost every other parameter, an equilibrium associated with an absolutely continuous stationary measure. And this has to be one of the following. Either chaotic sunspot equilibrium, or an orbit, a perfect foresight equilibrium path. So an orbit, a chaotic orbit of a backward perfect foresight map. Okay? So these are the equilibriums. So pretty much we remove an infinity of orbits from of indeterminate cycles. We remove an infinity of local sunspot equilibria associated with these indeterminate cycles, and we are left with one sunspot equilibrium, and we are left with trajectories with the backward of the. We are left with every perfect foresight equilibrium path. So, and now it's a question of interpretation. You can think there's infinitely many orbits, but all of these are dense on the interval. So, from my point of view, I see just one. So there's 2 equilibria coming out of here: the chaotic sunspot equilibrium and perfect foresight equilibrium paths, which are chaotic and dense on the interval. So that's the reduction we obtain. We eliminate infinitely many indeterminate cycles and the corresponding local sunspot equilibrium.
But I mean, you essentially only remove case 3, right?
No. So then it's not just case 3. Using this characterization, okay, what this says is that case 1 gives me the determinate cycles, and case 2 gives me essentially this thing, but I eliminate many more. So this tells me what the limit measure is.
The determinate cycle is the attractor of case 1.
Yeah, but so let me if you let me just go through the next example. So let me go then to an example, okay? So this is what I said. So let me go through an example. So let's consider this overlapping generation model. So you have a 2-period overlapping generation model. The agent's lifetime lasts for 2 periods. Population are constant. The proportions of young and old agents remain unchanged over time. And there's a representative agent whose preferences are given by an utility function of this kind. Okay, so this representative agent has some labor endowments, L1 star and L2 star. And there's some risk-free asset which evolves according to a difference equation of this kind. And we allow P of t and P t plus 1 to denote prices at 2 consecutive periods. Okay, Pt is known, Pt plus 1 is potentially random. So what we do is we solve a problem, an optimization problem like this, subject to some budget constraints. And this, the first order condition for these optimization problems gives us a condition like this. Now we rearrange the variables and we eventually get some map phi like this, which is precisely in the same form. So we bring everything to the same form as I shown you at the beginning. And now phi like this is a unimodal map given appropriate conditions on f and g, which are satisfied by utilities such as constant relative risk averse utilities or logarithmic utilities. So this kind of utilities ensure that phi defined in that way is a unimodal map and fits into that family of maps F. Okay, so phi looks something like this. It's not exactly the same shape as this, but it's still unimodal. And the figure I wanted to show you is this one. Okay, so now we go back to the equilibrium we were eliminating. So whoops, sorry about this. Okay. So the equilibria we end up eliminating are the red ones. So this is a bifurcation diagram for that backward perfect foresight map. So the theorem, what it was saying is that we are either in a case like this where all orbits converge to an attracting cycle, which is plotted in red. In this case is this green line. It's a steady state. Everything contracts to that point. In this case here, then there's a period doubling bifurcation. And you have a 2-cycle, then a 4-cycle, an 8-cycle. Then you get infinitely many cycles. But at some stage, the dynamics stop being regular. And you have case B, case 2, which is when you have an absolute continuous invariant measure. When you go to case B, you have infinitely many cycles, all of them repelling. These correspond to indeterminate cycles. All of these are eliminated. So what we really have is the blue. The blue corresponds to this absolutely continuous invariant measure. On top of this blue, we have 2 equilibria. Either a stochastic sunspot equilibrium, a chaotic sunspot equilibrium, as in the result by Araujo and Maldonado, or a perfect foresight equilibrium path that is dense over the interval. Okay, so I run out of time, but thank you.